Good morning. This is Dr. B. Geetavani. Today's session is about equivalence of push-down automata and context-free grammars. So in the previous two sessions, we have seen about the basics of the push-down automata and the equivalence of the push-down automata as L of M and N of M. Now, in this session, we will discuss about the equivalence of PDA and context-free grammar. Already we have discussed that the push-down automata are meant for accepting the context-free languages. So if a language is context-free language, definitely there will be a grammar generating that language, and that grammar is nothing but the context-free grammar. Context-free grammar, CFG. So for any context-free grammar, there will be normal forms. Two normal forms are there. Two normal forms will be there for the context-free grammar. One is the Greeback normal form. Another one is the Chomsky normal form. Greeback and Chomsky normal form. Greeback normal form abbreviated is GNF. This is known as the CNF. Now we will see, if a context-free language is given, how to construct the equivalent PDA accepting that particular language. So if L is a CFL, how to construct the PDA mission, the PDA M, which is accepting the L as N of M, that is by emptying the stack. So if L is a CFL, definitely there will be the corresponding CFG, and let us convert that CFG into the Greeback normal form, and let that converted Greeback normal form grammar is G is equal to VTPS. So this is the grammar given to us. So if the grammar is given, from this grammar we can construct its equivalent PDA. So from this given grammar, we can construct the PDA M as Q, T, V, delta, Q, S, pi. Already the original definition is M is equal to Q sigma tau delta Q naught Z naught F. F means here we are accepting the language by emptying the stack, so it is pi. So these are the 7 tuples present in the mission M. Here the capital Q is only Q. One single state is enough for the designing this PDA. And here the sigma input alphabet is nothing but the set of terminal states present in the grammar. In the grammar, T is a set of terminal symbols. So sigma is nothing but T. Now the third component is tau, that is stack alphabet. Stack alphabet is V. V is a set of variables present in the grammar. Delta rules, I will tell the delta rules. Next, initial state, Q naught. Q naught is, there will be only one state present in the mission, that is Q. So Q naught is Q only. And the initial stack symbol is nothing but the S. S in the grammar is nothing but the starting symbol of the production rules. S is the starting variable. And the last component is pi. Now the delta rule will be, the delta transition rules will be defined. Suppose in the grammar, if there is any production rule, A gives A gamma, then from this we have to write the transition rules like this. Delta of QAA is equal to Q gamma. That means by taking the state and applying the terminal symbol which is present as the first symbol in the production rule, and by taking the LHS variable of the production rule as a stack symbol, we are going to the state Q and we are replacing the stack by means of the gamma which is present in the production rule. The production rule is A gives A gamma. So from this A gives A gamma, we will write the delta transition rules like this. Delta of Q small a capital A is equal to Q comma gamma. So this is the way of constructing the PDA from the given CFG, which is in the Greeback normal form. So constructing the push-down automata from the CFG is very simple and easy. Now let us see an example for this one. The context-free grammar is given as follows. S gives 0 BB, B gives 0S, 1S, 0. Construct its equivalent push-down automata. So the grammar is given. If you observe the grammar's production rules, we can see that it is in the Greeback normal form only. So from this we have to construct the equivalent push-down automata. By recollecting the rules which I have told previously, now we can construct the PDA like this. The PDA M is equal to Q T V delta Q S pi, where delta is defined as delta of Q0S is equal to QBB. So we got this transition rule. From the production rule, S gives 0 BB. From this we got it. Next, from the production rule, B gives 0S. We will get the transition rule like this. Delta of Q0B is equal to QS. Next, one more production rule is there. B gives 1S. From this, the corresponding transition rule is Q comma 1 comma B is equal to Q comma S. And last production rule, B gives 0. From this, we will get the transition rule Q0B is equal to Q comma epsilon. So this is the way of constructing the push-down automata from the given context-free grammar. Now let us see the reverse of that one. That means if the push-down automata is given, how to construct the equivalent context-free grammar. Now the push-down automata PDA will be given. The PDA M is equal to Q sigma tau delta Q naught Z naught pi. This is the push-down automata accepting a particular language, and this is given to us. Now we can construct its equivalent context-free grammar directly from the given mission description as follows. So let the grammar G is equal to VTPS is the corresponding CFG, which is generating the language that is accepted by the given PDA. So here we can define the V, the set of variables of the form QAP, where Q and P are in Q, capital Q. From the set of states, we will pick each and every pair of the states Q and P and A in tau. Plus additionally, we will add one more symbol known as the S. Why? Because in any grammar, there will be a starting variable known as the S. So this is the set of the variables present in the grammar. So we can write, I will write clearly, V is equal to S union QAP, where QP are in Q, A belongs to tau. This is the V set. Next, T. T is nothing but the sigma. Set of terminals is equivalent to input alphabet sigma. Now production rules. We have to write the production rules from the given grammar. So from the given transition rules, we can generate the production rules as follows. So first rule, S gives Q naught, Z naught, Q for each Q in set of states Q. So we have to add new production rule. We have to keep new production rules of the form. S is the starting variable in the grammar. So S gives Q naught, Z naught and Q. Q naught is the initial state of the mission. Z naught is the initial stack symbol of mission. These two will be fixed, and the third component in this triple will be the state present in the capital Q. For each and every state, we have to write this S rules. Suppose if there are 3 states in the given mission, then 3 S production rules will come. Suppose if two states are there in the mission, 2 S production rules will come. Next, second rule of generating the production rules are if delta of QAA is equal to Q1 B1 B2 BM. Suppose this is the transition rule present in the given pushdown automata. Then from this transition rule, we have to generate the production rules. How to generate the production rules means QA QM plus 1 gives A Q1 B1 Q2 Q2 B2 Q3 so on QM BM QM plus 1. So from a single production rule of this form, we will get multiple production rules. So whatever be the state present in the transition rule will be kept here in the LHS in the first place, and whatever be the stack symbol that is present in the transition rule capital A, that will be the middle component in this variable. And the third component, see, observe the third component, it is your choice. You can pick any state from the capital Q here. I am writing it as a QM plus 1. It will give rise to, see, the input symbol that is applied in the transition rule have to be kept here, small a. Next, the resulting state will come as the first place, and the first input symbol, the first stack symbol B1, that will come here, and you have to take any state of your choice in the Q2 place, and the same Q2 has to be repeated. Next, Q2 B2, another state Q3, Q3 B3, Q4, Q4 B4, so on. So finally QM BM, and this component will be equivalent to the component which we have picked in the as the third component in the LHS variable, that is QM plus 1. So from a single production rule, from a single transition rule, we will get multiple production rules of this form. Next, another rule is there. If delta of QAZ is equal to Q prime epsilon, then from this sort of production rules, we will get the rule like this: QZ Q prime gives A. So these are the 3 rules which are used for generating the production rules from the given pushdown automata transitions. I will repeat the rules again. The first rule is we have to compulsory write the production rules with the starting variable. So starting variable is S. S gives Q naught Z naught Q for each Q in capital Q. Next, second rule is delta of QAA is equal to Q1 B1 B2 BM. If there is a such transition rule, from this transition rule we can generate the production rules of this form. So from a single rule, multiple production rules will be encountered. Next, third rule, if delta of QAZ is equal to Q prime epsilon, from this we will get the production rules of this form. QZ Q prime gives A. A single rule will come. Now let us see an example of constructing the grammar from the given NFF, given PDA, then you will understand well. Let the PDA mission is Q0, Q1, 0, 1, XZ, delta, Q0, Z0, Y, where delta is delta of Q0, 0, Z0 is equal to Q0 X Z0. Delta of Q0 0 X is equal to Q0 XX. Delta of Q0 1 X is equal to Q1 epsilon. Delta of Q1 1 X is equal to Q1 epsilon. Delta of Q1 epsilon X is equal to Q1 epsilon. Delta of Q1 epsilon Z is equal to Q1 epsilon. So this is a push down automata that is given. From this given push down automata, let us construct its equivalent context free grammar in the Greeback normal form, which is generating a language L that is accepted by this push down automata. So we know that G is equal to V T P S. So from the construction rules which we have discussed till now, we can define the V as V is equal to S, Q0 X Q0, Q0 X Q1, Q0 Z0 Q0, Q0 Z0 Q1, Q1 X Q0, Q1 X Q1, Q1 Z0 Q0, Q1 Z0 Q1. So there are two states, Q0 Q1, and two stack symbols X and Z0. So with these two combinations, we will get 8 different tuples. So Q0 X Q0, these are the different variables which we can generate from the given Q and given tau. Next, second component in the grammar is T. T is nothing but the input alphabet sigma, that is 0, 1. Next, third component of the grammar is a starting variable, that is S. S is equal to S only. Now we have to write the production rules. So let us write the production rules like this. So first we have to write the production rules, S rules. So S gives, according to our construction rule, it is nothing but the starting state, starting stack symbol, and any state from the given Q. So Q0, Z0, Q0 is the first rule. There is one more state in the given Q, that is Q1. So we will get another rule as Q0, Z0, Q1. Now, from each and every transition rule, we have to generate the production rules. Let us take the transition rule. Delta of Q1 1x is equal to Q1 comma epsilon. So from this transition rule, we will get the production rule of the form Q1x Q1 gives 1. Next, one more rule also there, which is giving the epsilon, that is Q0 1x, that is Q1 epsilon. So from this transition rule, we will get the production rule Q0 x Q1 gives 1. Here is the Q0, resulting state is Q1, and it is going to the, it is reading the symbol 1. So the corresponding production rule is Q0 x Q1 gives 1. Delta of Q1 epsilon x is equal to Q1 epsilon. So from this production rule, we will get, from this transition rule, we will get the production rule as Q1 x Q1 gives epsilon. That means here in the transition rule, it is not reading any input symbol. So we have to write the epsilon on the right side of the production rule. Next, delta of Q1 epsilon Z0 is equal to Q1 epsilon. From this transition rule, we will get the production rule as Q1 Z0 Q1 gives epsilon. Let us consider the another transition rule. Delta of Q0 0 Z0 is equal to Q0 x Z0. So from this production rule, from this transition rule, we will get multiple productions. So how means by following the second rule of the construction methodology. So Q0 Z0, the third component in this tuple will be our choice. I am picking the Q0 here. So Q0 gives, the input symbol will come here 0, the resulting state Q0, and the stack symbol X, and here the state is your choice. I am keeping the Q0 here, and whatever the state we have picked as the third component, now it will come as the first component here. So Q0, the next stack symbol Z0, and since this is the last variable, the third component of the LHS variable will come here. So it is Q0. Similarly, one more transition rule, Q0 Z0 Q0 gives 0, Q0 x. Now let us pick the another state which is present in the PDA machine. Now I am picking Q1. So here also Q1 will come, Z0, and the third component of the LHS variable have to placed here. So it is Q0. One more rule will come, Q0 Z0 Q1 gives 0, Q0 x Q0, Q0 Z0 Q1. And last production rule from this transition rule is Q0 Z0 Q1 gives 0, Q0 x. I am changing the state combination here as Q1. So Q1 Z0 Q1. So from this single transition rule, we will get 4 production rules of this form. Now let us take the another rule, Q0 0 x is equal to Q0 x x. It also gives rise to the 4 production rules of this form. Q0 x Q0 gives 0, resulting state is Q0 only, the initial stack symbol is X, and here it is our choice. I am taking the Q0 here, same Q0 will repeat here. Next stack symbol is X, and the state which is picked as the third component in the LHS variable is Q0. So we will write Q0 here. Next Q0 x Q0 gives 0, Q0 x. Here we are in the previous production rule we have taken Q0. Now we will take the Q1. Q1 x Q0. Next rule is Q0 x Q1 gives 0. Q0 x Q0. Q0 x Q1. Q0 x Q1 gives rise to 0. Q0 x Q1. Q1 x Q1. So by following the construction rule, from this single transition rule, we got 4 production rules of this form. So this is the required or obtained context-free grammar from the given pushdown automata. So if a pushdown automata is given, we can construct its equivalent context-free grammar. Similarly, if a context-free grammar is given, we can construct its equivalent pushdown automata. We have seen both the processes in this session. Thank you.